Sometimes when we do linear regression, because of the fact that the relationship in reality is not linear, the model that we get may not be as good as it could be. So there are two issues that I'd like to consider in this particular lesson: the issue of nonlinearity and heteroskedasticity. Let's take an example. So here is our good old autompg.csv data. So we've got the data file, and it has two columns called cylinders, which has got values like 3, 4, 5, 6, 8 and so on. I want to treat the cylinders column as a factor. Now, because of the fact that it's got numeric values, by default your R will treat the values as numeric, but suppose we don't want those values to be treated as numeric, we would have to explicitly convert them to factor. Of course, you need to do this only if the value looks numeric. If the value is actually textual, then when read.csv reads the data, it'll automatically convert it into a factor. Okay, so but if the values in the original CSV file are numbers, then by default R will treat the result also as a number. But in this case, if you want it to be treated as a factor, you've got to explicitly convert it. That's what we are doing here. Auto dollar cylinders is factor auto dollar cylinders. Similarly, there's another column called model year, which is also numeric, but for the purpose of this exercise, I want to treat that also as a factor. I don't want it to be treated as a number. I could very well have treated both of these as numbers and nothing bad would have happened, but I'm just illustrating the point that you might have to do this sometimes. Okay, so this time I am going to do partitioning and so on to illustrate the full cycle of what is going on. So we do library caret and we set the seed. I'm setting the seed to 2019, so if you want to replicate my results, you have to do the same. I'm doing generating the sample, and of course, because create data partition requires us to pass the target attribute so that it makes a proper mix of the target attribute in the training and test partitions. We do that, and then here is our training partition, here is our test partition. All this is very well understood by now, so there's really no need for me to spend any time on this. Okay, so now we build the linear regression model on the training data. Now, incidentally, column 8 contains the names of the cars. We don't want that in our linear regression model, obviously. So I say auto.lm is lm.mpg, which is the target attribute tilde dot, meaning all other attributes in the data set. And by the way, in the data set, I say train -8, right? So the data set is the training partition without the 8th column. The 8th column being the name of the car, which obviously doesn't play any role, right? So when you do this and you look at the summary of auto.lm, then you will see that the residual sum of squares, residual standard error, which is for us the RMSE, comes out as 2.8, and the R squared value of the regression comes out as 0.878. Okay, so this itself is pretty good. It's giving us quite good results. The R squared is pretty good, indicating that the regression is explaining quite a bit of the 87%, almost 90% of the variability in the data. So the model looks quite good, and it might actually be quite a useful model. But what I want to examine is to look at some characteristics of the model to see if we can do even better than this. Okay, so in order to do that, we plot the fitted values. Remember, the LM object has the fitted values, which means what? The predicted values for the training partition, and we want to plot them against the residuals, which are also contained in the linear regression model that we just built. Okay, so if you plot this, you will get a chart that looks something like this. So on the x-axis you have the fitted values, on the y-axis you have the residuals corresponding to each of those fitted values, right? Fitted values are basically the predicted values for each of the points. So for every point you've got the predicted values and you've got the corresponding residual, which is the difference between the actual value and the predicted value. Okay, so now this predicted value, the plot of predicted value versus the fitted value, is a useful plot. It's a very useful diagnostic plot for linear regression. Okay, now ideally this plot should not show any sort of trend at all. Okay, that means the values here should be distributed very evenly. It's just one big unpatterned blob. That's what this should be, but it's not. In this particular case, we are seeing a definite pattern of nonlinearity, right? So you can sort of, it's very hard not to see a curve that's going on here. On top of that, this is also showing another problem, which is that the variability of the residuals is increasing as we go from left to right. Okay, so this is actually showing you two problems. One is nonlinearity because of the fact that this implies a kind of a curve, and the fact that the variability of the residuals is increasing as we go from left to right, a kind of a funnel sort of a pattern. That is called heteroscedasticity. So this plot is actually showing you two problems in one. Now many times you'll see one or the other problem, but in this is a peculiar example where we are actually seeing both problems, right? So the moment you see this kind of a tendency in the plot of fitted values versus residuals, okay, then what that is telling you is that there is some nonlinearity in your model. Okay, that is, we fitted a linear model, but in reality there is some nonlinearity, and we can improve matters by transforming some of the variables. Okay, by transforming the variables, and shortly we'll see what do we mean by transforming the variables. Okay, now this variable transformation is actually somewhat of an experimental process, but I'll illustrate what is done here, right? So instead of fitting a linear model like this, what we'll try to do is to transform the target attribute. Okay, so the first thing I'm going to try to do is, instead of predicting the value, instead of building a model to predict MPG, let's try and build a model to predict the square root of the MPG, right? So what happens is that when you see a nonlinearity in the plot, when you use functions like square root and log, that will remove the nonlinearity to some extent. Okay, so other than the fact that the target is now square root of MPG, everything else is just the same as before. Okay, now for this new regression, let's plot the fitted values versus the residuals, and let's take a look at the summary of the plot, right? So when you do this, and of course let's calculate the RMS error as well, right? Now the reason I'm calculating the RMS error here and not just pulling it off of the regression is because now the regression is not calculating the MPG. The regression is calculating the square root of the MPG. So in order to calculate the RMSE, we'll have to take the regressed values or the fitted values, and we have to square them back again to get the actual MPG. So that is why when we're calculating the RMSE, I'm doing square root of mean of training $MPG minus auto.lm.square root, which is the name of the model here, $fitted values squared, right? Remember, the model is predicting only the square root now. So the fitted values that you get will be the square roots and not the actual MPGs. So in order to get the actual MPGs, we have to square it back, and that's what we are doing here. Okay, so we are calculating the mean of the deviation squared, taking the square root of that, that's the RMSE. So this time the RMSE comes out as 2.48, and the R square, which we plucked directly from the summary, is 0.901. Okay, so notice that the RMSE actually went down. Our earlier RMSE was 2.8 and our R square was 0.878. Now as a result of this transformation, we've got an improved RMSE to 2.48, and the R squared also improved to 0.901. Okay, so the model actually improved simply by performing a simple nonlinear transformation. Okay, and now when you plot the fitted values with the residuals, you see the trend is not disappeared entirely, but it's much better than it used to be. Right here also we see a very slight trend, but it's not as pronounced as it earlier was. Okay, so the pattern is less prominent. Now, one of the other transformations other than square root, which is also very effective in smoothing out nonlinearities, is what is called as the logarithmic transformation. So this time, instead of square root of MPG, let's do log of MPG. The log function is even more powerful than the square root function in removing nonlinearities. Okay, so other than saying log MPG, everything else is just the same as before. So now once again we can plot the fitted values and the residuals, and we can calculate the RMS error. This time, since this is calculating the logs, the fitted values are now the logarithms of the MPG. In order to get the predicted values, you now have to exponentiate them. Okay, so you take the fitted value and apply the exponential function to it to get back the predicted MPG. And then, of course, other than that, it's just the same as before. I'm just calling it rmsc.log, and we call the model as auto.lm.log. Okay, so this time you see the RMSE has improved even further from 2.48 to 2.39, and the R square improved even further to 0.915. Okay, so clearly this the transformations that we applied to the target attribute have definitely produced benefits for us in terms of improving the model. Of course, the model was pretty good as it is. Nevertheless, why not take improvements like this, which are coming practically for free? Okay, so now you can see the trend has vanished even more. There's still, you could say, a very slight trend, but nobody would complain if you treated this as not showing any pattern or any trend. Okay, so there is almost no pattern at this point. Okay, let's see how we perform on the test partition. Remember, all of this stuff that we are doing is only on the training partition, but the proof of the pudding is in the test partition. So let's take a look at how the system is performing on the test partition. So let's generate the predictions on the test partition. So this time I'm going to generate the predictions using our original linear model, and then the square root transformation, and then the log transformation. So first let's do the original model. Predict.test. Pred.test is predict auto.lm test minus 8, and then we calculate the RMS error on the test partition. Okay, so the basic model is giving us an RMS error of 3.56. This is the model which is a complete linear model, the auto.lm, no transformation. Okay, now let's take a look at the square root transformation. Once again, we generate the predictions using the square root transformation, and on the test partition, of course, the results are all the square root, the predicted values. So in order to compute the RMS error, we have to square the values, and that's what I'm doing here. Pred.test.square root is squared. Now you can see the RMS error is less. So the fit is better, 3.56 to 3.41. Finally, let's look at the logarithmic model, which is the same thing, except that this time we need to raise it to the exponential, and the RMS error goes down further to 3.29. Okay, so not only did the model perform well on the training partition, model also performed well, better, the transformed model also performed better on the test partition. So let's summarize what we have studied here with a generic example. So when you plot the fitted values against the residuals, you ideally want a pattern which looks something like this, right? In other words, the fitted values and residuals doesn't show any pattern. The values are just strewn around all over the place. There is absolutely no pattern. Okay, this is ideal. Now this is a case where you see heteroskedasticity, which means the variability is increasing as the fitted values are increasing. So you're seeing a pattern here. Of course, it might go the other way also. They may decrease, but you see a funnel pattern of some kind. That's a clear indication of heteroskedasticity. This is a case where the pattern is actually curvilinear when you see nonlinearity. Okay, so in both of these cases, heteroskedasticity and nonlinearity, what we can try and do is to do exactly what I showed you earlier, which is try to fit a linear model for the transformed values. Okay. Now most of the time transforming the target attribute works well, but sometimes you may have to transform not the target attribute but one or more of the predictor attributes, or sometimes you may have to transform both target attribute and some predictor attributes. Okay. Now how do you know which one to do? Well, I think a good rule of thumb is to first try to transform the target attribute. If that doesn't do the job for you, then take a look at the relationship of the target attribute with each of the predictor attributes. And if you see any nonlinearity in any one or more of those relationships, try transforming the predictors instead of the target. Okay, so a logarithmic predictor works well. So try that and see what results you get. So this process is somewhat exploratory. So that's the general approach of handling heteroscedasticity and nonlinearity in linear regression models. Now, one other thing that you will sometimes hear when we are talking about the quality of a linear model is something called multicollinearity, right? You have the situation of multicollinearity when one or more of the predictors are highly correlated with each other. Okay, so when you have that, linear models exhibit certain undesirable behaviors. But fortunately for us, when using linear models in a strictly predictive scenario like we are doing, it doesn't matter. Multicollinearity doesn't affect us if our sole goal, sole aim is to perform predictions. Okay, so therefore, since it has not much of a role to play in prediction, I'm not discussing multicollinearity in any great depth.